Hello everyone and welcome to my poster presentation. I am Nujhat, a fourth year graduate student at Georgia Tech. I will be talking about our experiments on trap capture and emission dynamics in ferroelectric field effect transistors and their impact on device operation and reliability. Our task is aligned with theme 4 of ASCENT, which is Smart Logic Memory Fabric. Over the past decades, the memory speed is not improving as much as the processor speed. Now, a game changer for all data-centric applications will be the high-performance embedded memory, which shares the same silicon as its logic counterpart, hence enables efficient data transfer and can support in-memory computing architecture. Ferroelectric-based memory is one of the several emerging candidates for the embedded memory applications. The charge voltage characteristics of a ferroelectric capacitor shows hysteresis, which means that this can be used as a non-volatile memory device. Now, when we use this Fe material in the gate dielectric of a transistor, we get a ferroelectric FET, which has been used in the past years in non-volatile memory applications. A major drawback of these FeFETs is its endurance. Previous reports have shown that although a ferroelectric capacitors show endurance up to around 10 to the power 10 cycles, FeFETs endurance is only around 10 to the power 5 cycles. This proves that ferroelectric polarization to PR is not the only indicator of the FeFETs performance, and we need to understand the defect and trap dynamics during the cycling operation as well in order to optimize the ferroelectric FETs design to move towards better endurance, which is what our task is based on. First, we fabricate ferroelectric FETs with 10 nanometer hafnium zirconium oxide with the process flow shown here. The HRTM image of the FeFET gate stack shows clear interfaces. To track electron and hole dynamics during write operation, we separately and simultaneously measure transient currents through body source and drain terminals using the setup shown here with triangular Pond waveform applied to the gate. Polarization charge through the gate, hole charge through the body, and electron charge through S and D are all calculated by integrating current transients. While gate polarization captures ferroelectric switching charge through the gate, QB and QSD account for polarization components carried by holes and electrons respectively in the channel and reflect trapping effects. Next, we did the FeFET endurance measurement. Along with measuring the IDVG characteristics of the FeFET at each cycling decades, we also applied the split PV method to track the electron and hole trap dynamics in the FeFET during the cycling operation. We see that a memory window starts decreasing at 10 to the power 3 cycles and vanishes at around 10 to the power 5, although the 2PR is unchanged until 10 to the power 5 cycles. Interestingly, the amount of emitted holes and electrons also decreases with cycling. This can also be seen from this figure as well, where you can see that emitted holes and electrons are decreasing with cycling, although the 2PR value is almost unchanged. This indicates that electron and hole dynamics play a very big role in FeFETs operation. The universality of the suggested mechanism can be confirmed in FeFETs fabricated in different facilities. We see that in all three of these devices, 2PR are significantly different. Yet, memory window for all three of them shows similar degradation characteristics beyond 10 to the power 3 cycles. We also see that as emitted holes approach 0 with cycling, memory window also does the same due to charges not being able to be emitted. With cycling, the decrease in high threshold voltage with the decrease of hole emission indicates that more holes are being trapped for longer periods of time. Also, emitted holes declining with the increase of NIT suggests that increase in the trap density with the band gap increases the time constant. We have successfully fabricated and analyzed ferroelectric FETs. We now have an intuitive model as how the FeFETs operates. Based on this, we plan to build a quantitative model by this year. We also plan to exploit our model to optimize the FeFET design for better performance. Thank you all for listening.